14 seconds. That is the number space agencies don't like putting on posters. 14 seconds is roughly how long a healthy adult can be exposed to raw, unprotected space and still have a real chance of walking away from it. Not comfortably, not painlessly, but alive. Add 10 more seconds to that number and the outcome changes completely. And there's almost nothing your body can do to buy you extra time once that clock starts running. If you have ever imagined stepping outside an airlock without a suit, and just holding your breath for a minute, waiting it out, toughing through it the way you'd hold your breath underwater, what actually happens to a human body in those 14 seconds is going to change the way you think about space forever. We like to imagine deep space as empty, a calm, silent nothing stretched between glowing planets. That image is comforting, and it is almost completely wrong. Empty is not the same as safe. Empty is, in some ways, the least dangerous thing about it. What's actually out there is a combination of forces working against the human body from every possible direction at the same time, and every single one of them is lethal on its own. Pressure disappearing in an instant. Temperature behaving in ways that break every intuition you've built up living on this planet. Radiation pouring through you constantly, undetected, doing damage you won't notice for years. And distances so enormous that even our fastest machines would need longer than the entire span of recorded human history just to reach our nearest star. None of this is exaggeration for the sake of drama. It's what happens when you take a body that's spent hundreds of thousands of years being shaped by one very specific, very narrow set of conditions, and you remove every single one of those conditions at once. So let's actually understand what those conditions are, because most people have never had a reason to think about them. Right now, wherever you're sitting, air is pressing against your entire body, about 14.5 pounds on every square inch of you. Over your whole body surface, that adds up to something in the neighborhood of 20 tons of force. You don't feel it because your body pushes back with equal pressure from the inside. Your blood, your lung tissue, the fluid in your eyes, all of it exists in a careful balance with the air pressure around you. Your lungs work because of a pressure difference your diaphragm creates every time you breathe. Your blood carries dissolved gases that stay dissolved specifically because there's enough outside pressure holding them there. This isn't a minor background detail of being alive. It is one of the load-bearing pillars the rest of your biology is built on top of. Now take that pillar away instantly and completely, and you get vacuum exposure, and the first thing worth knowing is that your body starts reacting to it in well under a single second. The moment external pressure disappears, gases dissolved in your blood, and tissues start coming out of solution, exactly the way carbon dioxide rushes out of a shaken soda can the instant you crack the seal. Except, this isn't happening in a bottle where the bubbles just rise harmlessly to the surface. It's happening inside your bloodstream, inside your joints, inside the soft tissue of your organs, all at once. Doctors call this ebullism, and it is functionally the most extreme case of decompression sickness that exists. The same family of injury deep sea divers fear if they surface too fast. Except, instead of going from a few atmospheres down to one, you're going from 1 atmosphere straight to 0 in an instant. There is no gradual version of this. It happens everywhere in your body simultaneously. At the same moment, something even stranger starts happening to the moisture in your body. Water's boiling point isn't fixed. It depends entirely on the pressure pushing down on it. At the top of Mount Everest, where the air is roughly a third as thick as at sea level, water boils at around 68 degrees Celsius instead of 100. In a true vacuum, with essentially zero external pressure, water can turn to vapor at your normal body temperature without any added heat at all. That means the saliva on your tongue, the fluid on the surface of your eyes, the moisture in your mouth and throat, all of it would begin flash boiling away almost immediately. Not violently, like a pot bubbling on a stove. More like an aggressive, rapid evaporation you would feel instantly and could do absolutely nothing to stop. If you happen to be holding your breath the moment this started, the outcome gets worse, even faster. Air trapped in your lungs would try to expand to fill the emptiness around you, and lung tissue simply cannot survive that kind of expansion. It tears. This is the exact reason scuba instructors drill into every student that you never, under any circumstance, hold your breath while ascending. Even the pressure difference between 10 meters underwater and the surface, which is a single extra atmosphere, can rupture lung tissue if you hold your breath while rising. Going from a full atmosphere to true vacuum is an enormously larger jump than that. Here's the part that surprises almost everyone. Even if you exhaled instantly and did everything textbook perfect, you would only buy yourself a handful of extra seconds. Because the ebullism and the oxygen problem are already running in the background, regardless of what your lungs are doing. Your brain, despite weighing only about 2% of your total body mass, burns through roughly 20% of the oxygen your body uses. It is an incredibly hungry organ that has almost no tolerance for interruption. Under normal circumstances, holding your breath, you might last close to a minute before losing consciousness, longer if you're trained for it, because your blood is still oxygenated and there's residual air still in your lungs doing useful work. In vacuum, none of that applies. There's no air left in your lungs. Your blood is starting to foam from the gas bubbles forming inside it, which cripples its ability to carry oxygen even if there were oxygen available to carry. Consciousness fades in around 10 to 15 seconds. Not minutes, seconds. That's simply how long the oxygen already circulating in your bloodstream takes to run out under this kind of stress. After that, you're unconscious. And the timeline for what follows has actually been documented, pieced together from vacuum chamber accidents, animal studies, and the raw physics involved. In the first couple of seconds, gas already starts expanding under the skin, causing visible swelling. Around the 6-second mark, circulation starts becoming compromised as bubbles physically interfere with blood flow. By 10 seconds, brain oxygen has dropped below the level needed to sustain awareness, and vision and hearing begin collapsing inward. By roughly 30 seconds, swelling throughout the body becomes pronounced enough that a person would appear visibly bloated to anyone watching. By the 1-minute mark, oxygen deprivation to the brain is starting to cause damage that would very likely be permanent, even with immediate rescue. By 90 seconds, cardiac function is failing outright, and by 2 minutes, it's over. No heartbeat, no brain activity, no possibility of revival. This isn't a worst-case guess pulled from a science fiction writer's imagination. In 1965, a technician testing a prototype spacesuit inside a vacuum chamber at what's now NASA's Johnson Space Center experienced a suit failure that exposed him to near-vacuum conditions. He later described feeling the moisture on his tongue begin to boil in the instant before he lost consciousness. Chamber operators noticed the failure and repressurized the room within about 14 seconds. He woke up shortly after and made a full recovery with no lasting damage. 14 seconds. That is the actual, documented ceiling for a survivable exposure. And it only worked because there was a wall, a control room, and a team of people close enough to fix the problem immediately. In genuine deep space, none of those things exist. There's no chamber to repressurize. There's no team standing by. There's just an unbroken, unlimited vacuum in every direction, and once you're in it, the clock doesn't stop for anyone. If you're watching this and trying to guess how long you personally think you'd stay conscious before reading further, drop your guess in the comments, because most people are wildly off in one direction or the other, and it's honestly one of the more interesting things to see people argue about below this video. Pressure and oxygen alone would be enough to make deep space lethal, but they are only the first item on a much longer list. And the next one, temperature, breaks almost every assumption people carry into this topic from movies. Most people picture space as the coldest possible environment, somewhere close to absolute zero, and assume that stepping outside a spacecraft without protection would freeze a person solid within moments, the way it's often shown on screen. The real physics tells a very different story. Temperature is fundamentally a measurement of how fast molecules are moving and colliding with each other. And in a true vacuum, there are so few molecules present that the entire concept starts to break down. What does exist is thermal radiation, the background glow left over from the early universe, sitting at a bone-chilling few degrees above absolute zero. That environment is lethal eventually, but not instantly, and the reason has to do with how heat actually leaves a human body. On Earth, you lose heat three ways: conduction, through direct contact with something colder; convection, through moving air or water, carrying warmth away from you; and radiation, through infrared light leaving your skin. In a vacuum, conduction and convection simply don't function because there's no surrounding matter to conduct into or convect through. Radiation is the only mechanism left, and radiation is a comparatively slow process for something sitting at normal body temperature. Left completely alone in deep space, with unlimited oxygen and perfect pressure protection but zero insulation, a person would indeed eventually freeze to death. But it would take hours, not seconds, and long before hypothermia became the relevant threat. The effects of vacuum exposure and oxygen deprivation would have already ended things. The instant freeze scene from countless movies is quite simply fiction. There's an opposite problem too, one that gets far less attention. Anywhere close to a star, you're being bombarded with intense direct radiation, with nothing scattering or filtering it the way an atmosphere normally would. Near Earth's orbit, roughly 1,360 watts of solar energy hit every square meter facing the sun. Without an atmosphere to spread that heat around, one side of an exposed object or body would heat dramatically while the opposite side, facing away into the cold of space, would drop just as dramatically. You'd get an extreme temperature split across a single body at the same moment. Sunlit surfaces climbing well above the boiling point of water, while shadowed surfaces plunge far below freezing. It's a genuinely bizarre problem, being simultaneously too hot and too cold on different sides of yourself. And it's one more variable engineers have to design around for every single spacecraft and suit ever built. And that's still not the most dangerous thing hiding in deep space. The most dangerous thing is radiation, and not the kind most people picture. Earth's magnetic field and atmosphere work together as an almost invisible, thoroughly underappreciated shield. The magnetic field deflects charged particles toward the poles, where they light up the sky as auroras instead of striking the surface. The atmosphere absorbs the bulk of incoming ultraviolet, X-ray, and gamma radiation before it ever reaches you. Strip both of those protections away, and you're left facing two distinct threats. The first is solar radiation, the ultraviolet light, X-rays, and occasional violent bursts of charged particles thrown out by the sun during flares and coronal mass ejections. Unshielded, ultraviolet exposure alone would cause severe skin damage within minutes, not from heat, but from direct cellular destruction at the molecular level. The second threat, and by far the more serious one, is galactic cosmic radiation. These are atomic nuclei, mostly stripped protons, but sometimes heavier elements, flung across the galaxy by supernova explosions and other extraordinarily violent cosmic events, accelerate to speeds approaching the speed of light. A single one of these particles carries energy that dwarfs anything produced inside our most powerful particle accelerators on Earth. When one strikes human tissue, it doesn't just damage the cell it hits directly. It rips electrons off atoms along its path, shatters strands of DNA, and often triggers a cascade of secondary particles that spread the damage even further. Your body has repair mechanisms for this kind of thing under normal circumstances. And on Earth, shielded by the magnetic field and atmosphere, you absorb an almost negligible dose over your entire lifetime. In orbit, that changes fast. Astronauts on the International Space Station, still partially protected because they remain inside Earth's magnetic field, absorb radiation at somewhere around 50 times the surface rate. A 6-month rotation on the station measurably increases lifetime cancer risk. Push beyond that magnetic boundary entirely, the way the Apollo astronauts briefly did on their trips to the moon, and the exposure rises sharply again. NASA's own estimates suggest a round-trip mission to Mars, using current shielding technology would come uncomfortably close to or potentially exceed the career radiation limits the agency currently sets for its astronauts, largely because of galactic cosmic rays that punch straight through conventional shielding materials, and in some cases actually create additional secondary radiation when they collide with the very metal meant to stop them. This is the uncomfortable part engineers rarely get asked about directly. You would assume thicker walls simply solve the problem, and to a limited extent they do. But cosmic rays are energetic enough to punch through meters of solid material, and every extra kilogram of shielding has to be launched from Earth's surface first, which multiplies fuel requirements dramatically. Water actually shields better than metal against this specific threat, because it doesn't shatter into as many dangerous secondary particles on impact. But protecting a crew properly would require several meters of water surrounding their living space, which translates into an amount of mass that no current rocket design can practically lift and accelerate. So spacecraft designers are stuck making an uncomfortable trade every single time. More shielding buys safety and costs mass, fuel, and money. Less shielding saves resources and accepts a measurable increase in cancer risk for the crew. There is currently no version of this trade that fully solves the problem. You can only choose which direction you're willing to compromise in. Now, pause for a second and think about everything we've covered so far: pressure, oxygen, temperature, and radiation, and realize we haven't even reached the part of this story where humans actually try to build technology to survive out there. Because that's where an entirely new category of danger begins. A spacesuit is, in every meaningful sense, a tiny personal spacecraft, and it has to solve every problem we just described simultaneously in a package a person can actually move around in. NASA's current suits maintain internal pressure at around 4.3 pounds per square inch, deliberately lower than Earth's normal atmospheric pressure, because lower pressure means a suit that's easier to bend and move in. But you can't drop that number too far, because the astronaut still needs enough oxygen partial pressure to breathe properly. So the suits use pure oxygen instead of a nitrogen mix to keep the numbers workable. That decision solves one problem and immediately creates another, because pure oxygen environments are an extreme fire hazard. Any spark, any static discharge, any unexpected heat source can ignite materials that wouldn't burn at all in ordinary air. This isn't a theoretical concern. In January 1967, during a routine ground test, a spark inside the Apollo 1 command module, pressurized with pure oxygen at a level even higher than modern suits use, ignited materials inside the cabin. The fire spread in seconds. The hatch design at the time required internal pressure to drop before it could be opened, and it couldn't be opened quickly enough. All three astronauts aboard, Virgil Grissom, Edward White, and Roger Chaffee, died before rescue crews could reach them. That single tragedy completely reshaped how spacecraft cabins and hatches have been designed ever since, and it's a stark, permanent reminder of just how unforgiving these environments are the moment something goes even slightly wrong. Beyond the fire risk, a suit has to continuously supply fresh oxygen and scrub away exhaled carbon dioxide, usually using canisters filled with lithium hydroxide that chemically bind CO2 into a solid compound. Those canisters have a fixed capacity. Once they're saturated, they stop working and carbon dioxide starts accumulating, which causes dizziness, confusion, and eventually loss of consciousness if it isn't addressed. A typical spacewalk is limited to somewhere around 6 to 8 hours specifically because of this ceiling. Temperature management inside a suit is its own separate nightmare. The human body constantly generates heat, and in a vacuum that heat has nowhere to go except through radiation, which is slow and inefficient. Left unmanaged, an astronaut working hard inside a sealed suit would start overheating within minutes. Modern suits solve this with a liquid cooling garment. Essentially underwear woven through with tubing that circulates cool water against the skin, carrying heat away to a radiator built into the suit's backpack. It works, but it's mechanically complex, and if the cooling system fails, an astronaut might have as little as 10 to 15 minutes before heat buildup becomes genuinely dangerous. In 2013, Italian astronaut Luca Parmitano experienced exactly this kind of failure during a spacewalk when water from a malfunctioning cooling system began leaking directly into his helmet. In zero gravity, water doesn't drain away, it simply floats and spreads, and it began covering his eyes, his nose, and eventually threatened his ability to breathe. He had to navigate back to the airlock essentially blind, guided partly by memory and partly by touch, while the leak continued the entire way. By the time his helmet was finally removed, over a liter of water had accumulated inside it. He came remarkably close to drowning, inside a sealed suit, in the vacuum of space. It's one of the clearest examples of how a single mechanical failure, something that would be a minor inconvenience on Earth, can become a life-threatening emergency the instant it happens somewhere with zero margin for error. Even the gloves cause real, physical damage over time. Working against constant internal pressure with every finger movement, astronauts routinely report hand fatigue, cramping, and in some documented cases, actual fingernail loss from the sustained pressure of gripping tools for hours at a time. A modern NASA suit weighs close to 280 pounds fully assembled, costs millions of dollars, and most of the units still in active use were originally built in the 1980s and 1990s, refurbished repeatedly because designing an entirely new suit from scratch takes years of testing to certify as safe. Every single system inside it, pressure, oxygen, temperature, mobility, communications, has to work flawlessly because there is no backup plan for a suit failure hundreds of kilometers above the ground. Now scale all of this up from a single suit to an entire spacecraft, because the same fragility just gets bigger, not safer. A pressurized spacecraft hull is often only a few millimeters thick. That's a deliberate design choice, not an oversight, because every additional kilogram of structure requires additional fuel to launch it, and that fuel itself needs even more fuel to lift it. In a compounding relationship engineers call the rocket equation, it's merciless. For a typical rocket launch, only a small single-digit percentage of the total launch mass actually reaches orbit as usable payload. Everything else is fuel and structure discarded along the way. That's the mathematical reason spacecraft can never simply be built thicker and safer without limit. Mass is the enemy of every single mission, which means the thin hull separating a crew from the vacuum outside is also their only real barrier against space debris, and debris is a far bigger problem than most people assume. In May 2021, a piece of debris smaller than a pencil eraser struck Canadarm2, the International Space Station's robotic arm, at a relative speed above 25,000 kilometers per hour. It punched clean through the arm's thermal blanket and left a small but real puncture in the metal boom underneath. Nobody on board felt it happen or heard it happen. It was only discovered days later during a routine inspection. That same year, in October, a separate micrometeorite strike hit the station's Russian Nauka module, puncturing a radiator and venting over 70 liters of coolant directly into space before the leak could be brought under control. A 2021 NASA Inspector General report estimated that low Earth orbit alone contains more than 26,000 pieces of debris large enough to destroy a satellite outright, over 500,000 pieces roughly the size of a marble capable of seriously damaging a spacecraft, and more than 100 million fragments as small as a grain of salt, still large enough to puncture a suit or a thin hull. And this is happening in the single region of space humanity actually monitors closely, where ground stations track tens of thousands of objects in real time and can command the station to maneuver away from anything large enough to be seen coming. The moment you leave that monitored bubble and head into deep space, none of that protection exists anymore. There's no tracking network millions of kilometers from Earth, no warning, No possibility of an evasive maneuver against something you never saw coming, and a strike on the wrong system, a power line, a water recycling unit, a whole section, could end a mission instantly with no way to fully explain what happened afterward. Even setting debris aside entirely, simply keeping a crew fed, watered, and breathing without any possibility of resupply is its own enormous unsolved problem. Every drop of water, every breath of oxygen, and every gram of food a crew consumes either has to be carried from Earth in advance or produced and recycled on board. And current recycling technology, even at its very best, still isn't perfect. The International Space Station's life support system spent roughly its first decade recovering somewhere around 93 to 94% of the water astronauts used. In 2023, engineers finally pushed that figure up to a genuine milestone of 98%. By adding new equipment specifically designed to extract the last usable water from what had previously been discarded waste. That's a remarkable achievement, but stretch that same small remaining loss out across a mission lasting years instead of months. And even a 2% shortfall compounds into a real, unavoidable resource deficit that no amount of careful rationing can eliminate. It can only be delayed. The instinct to simply pack more supplies runs straight back into that same brutal rocket equation. Every extra kilogram of food or water needs fuel to launch, fuel to accelerate, and fuel to decelerate, in a spiral that grows worse the more total mass you try to carry, which means the resource problem and the propulsion problem aren't actually two separate issues at all. They're the same underlying problem viewed from two different angles, and neither has a clean, independent fix with current technology. The most vivid warning about exactly how difficult a fully self-contained life support system really is didn't come from space at all. It came from a facility built on the ground in the Arizona desert. In September 1991, 8 people sealed themselves inside Biosphere 2, a 3-acre glass and steel structure specifically designed to test whether a completely closed artificial ecosystem could sustain human life indefinitely, with the explicit long-term goal of understanding what a future Mars habitat or deep space vessel would actually require. Within the first 16 months, oxygen levels inside the sealed structure steadily dropped from a normal near 21% down to roughly 14%, a concentration comparable to standing on a mountain over 4,000 meters high. Crew members reported persistent fatigue, difficulty concentrating, and disrupted sleep. It took months of investigation to find the cause, and the answer turned out to be almost absurdly mundane. Soil microbes inside the sealed structure, feeding on unusually rich organic material in the imported soil, were consuming oxygen and producing carbon dioxide far faster than the plant life inside could photosynthesize it back out, while the facility's own concrete was simultaneously absorbing carbon dioxide directly out of the air through an ordinary chemical reaction nobody had planned for. Engineers eventually had to pump in emergency oxygen from outside, quietly breaking the single rule the entire 2-year experiment had been built around. It wasn't proof that closed ecosystems are impossible. It was proof that a sealed environment includes literally everything inside it, down to the bacteria living in the soil and the chemistry happening inside the walls, and any single one of those things can throw the entire balance off in ways nobody predicted. On a planet where, if something goes wrong, you can still open a door and walk outside. In deep space, there is no door. If you've made it this far, this is genuinely the point in the video where most people underestimate what's left, because everything so far has been about the spacecraft. What comes next is what happens to the human body itself, independent of any equipment failure at all, just from existing in this environment for an extended period of time. Remove Earth's gravity for months or years, and the human body starts treating its own skeleton as unnecessary weight. Astronauts consistently lose bone mineral density at a rate of roughly 1 to 2% per month, while weightless. Concentrated most heavily in exactly the weight-bearing bones a person would need most upon returning to any planetary surface, the hips, the spine, and the legs. Extrapolate that rate honestly across a period of years rather than months, and the numbers become genuinely alarming. A real possibility of losing somewhere between a third and more than half of total bone density over the course of a multi-year mission, even accounting for the roughly 2 hours of daily resistance exercise astronauts currently use to slow, though never fully stop, the decline. Muscle mass follows a similar path, atrophying without the constant resistance of gravity, particularly in the legs, back, and core, which happen to be exactly the muscle groups needed simply to stand upright again afterward. The heart, itself a muscle, undergoes its own quiet transformation over time, gradually losing mass and shifting shape as it adapts to no longer needing to pump blood upward against gravity's pull. An adaptation that becomes a genuine liability the moment that same heart has to suddenly work against gravity again, whether on a planet's surface or back home on Earth. Astronauts returning from even standard 6-month missions frequently experience dizziness, a racing heartbeat, and occasional fainting spells simply from standing up too quickly in the days after landing. Fluid inside the body, no longer pulled downward, shifts upward toward the head and chest, producing a puffy, swollen appearance astronauts have informally nicknamed puffy face syndrome, along with a persistent stuffy nose sensation that never fully resolves for the length of the mission. That same upward fluid shift raises pressure inside the skull, and NASA has documented real, sometimes lasting structural changes to the eye as a result, involving swelling of the optic nerve and, in some astronauts, an actual flattening of the back of the eyeball, producing vision changes that in a meaningful number of documented cases have persisted for years after returning to Earth, and in a smaller number of cases appear to be permanent. The immune system weakens too, measurably, with multiple studies documenting the reactivation of ordinarily dormant viruses, including strains related to chickenpox and herpes, in astronauts during extended spaceflight. Even something as small as a minor cut heals more slowly in orbit than the same wound would on the ground. A detail that sounds minor in isolation, but becomes far more serious once you stack it alongside everything else, already working against a crew's health across a mission lasting years rather than months. And underneath every one of these physical symptoms sits a psychological weight that's arguably just as serious and considerably harder to measure or treat from a distance. Confined for years inside a small sealed environment, with no ability to step outside, feel actual wind, or meaningfully vary the daily routine, astronauts on even relatively short missions have reported documented struggles with sleep disruption, since there's no natural day and night cycle to anchor the body's internal clock. Alongside measurable periods of anxiety, low mood, and cognitive fog. Ground-based isolation research, including studies conducted at NASA's Hera facility, a sealed habitat specifically built to simulate the confinement and mission stress of long-duration deep space flight, has consistently found that even carefully screened, extensively trained volunteers show real signs of psychological strain the longer an isolation period stretches on. Researchers running similar isolation studies at Antarctic research stations have identified a recurring pattern they call the third quarter phenomenon, a measurable dip in morale that tends to appear once a mission is well past its midpoint, but still has a considerable stretch left to go. And every single one of these ground-based studies still includes something a true deep space mission never would: a genuine emergency exit. A door that can be opened if something goes seriously wrong. There is no equivalent option once you're actually out there. No early return, no emergency evacuation, no stepping outside, even for a few minutes, for relief from the same four walls, the same faces, and the same manufactured lighting, for as long as the mission requires. Now here's where the scale of this problem gets almost impossible to hold in your head properly, because everything described so far assumes a relatively short trip, something on the order of a mission to Mars. Push the destination out further, and the numbers stop being merely difficult and start becoming almost absurd. power itself becomes a crisis the farther you travel from the sun, because of something called the inverse square law. Move twice as far from a light source and its intensity doesn't drop by half, it drops by a factor of 4. Move 10 times farther, and it collapses by a factor of 100. At Earth's distance from the sun, solar panels work extremely well. By the time you reach Jupiter, roughly 5 times farther out, available sunlight has dropped to around 4% of what we receive here. Push out to Neptune, 30 times farther than Earth, and that number collapses to 0.1%. Beyond the edge of the solar system, in true interstellar space, sunlight becomes so faint, it's functionally useless as a power source at all. The obvious fallback is nuclear power, and it works, up to a point. NASA's Voyager probes, launched in 1977, have survived for nearly 5 decades using radioisotope generators that convert the natural heat of decaying plutonium directly into electricity, requiring no sunlight and no moving parts at all. But that heat source has a fixed decay rate. Plutonium loses roughly half its output every 87 years, meaning Voyager's available power has been shrinking continuously since the moment it launched. Engineers have already had to permanently shut down individual instruments on both spacecraft, one by one, specifically to conserve the shrinking power that remains. Even a nuclear power source, in other words, isn't truly permanent. It's a very long, very slow countdown, and for an unmanned probe, losing power means losing an instrument. For a human crew, it means losing heat, breathable air, and drinkable water simultaneously, with nowhere else to draw any of it from. And then there's simple distance. The nearest star system beyond our own, Alpha Centauri, sits roughly 4.24 light-years away. NASA's Parker Solar Probe, the fastest object humanity has ever built, reaches speeds of around 690,000 kilometers an hour at its closest approach to the sun. Sustained continuously in a straight line, at that speed, the trip to our nearest stellar neighbor would take more than 6,000 years. That number isn't a dramatic exaggeration. It's the honest answer using the single fastest machine humanity has ever launched. Every problem covered in this video, the power fall-off, the resource recycling, the debris risk, the radiation exposure, the physical toll on the human body would need to be sustained not for a few years, but for a length of time that dwarfs the entire span of recorded human civilization. Before a crew traveling anywhere near our current technological limits would ever reach even the closest star system beyond our own. None of this means humanity is permanently locked out of deep space, and it's worth being precise about what all of this actually proves versus what it doesn't. Every limitation described here is rooted in today's specific technology and today's specific medical countermeasures, not some permanent, unchangeable law of nature the way the speed of light is. Better shielding materials, more efficient closed-loop life support systems built directly on the hard lessons from both the ISS and Biosphere 2, artificial gravity generated through rotation, and improved countermeasures for bone and muscle loss are all active, funded areas of ongoing research, not abandoned dead ends. Engineers have studied rotating spacecraft designs capable of simulating Earth-like gravity since at least the 1960s, and the underlying physics isn't seriously disputed by anyone. What's missing isn't the theory, it's an actual vehicle built and flight tested at the scale required to make the concept work comfortably over a period of years, something no space agency has yet attempted. Radiation researchers continue testing new shielding materials, including hydrogen-rich polymers and strategically placed water. Though none of these approaches yet fully solves the problem posed by the highest energy galactic cosmic rays specifically. But it would be dishonest to pretend those solutions already exist, in a form ready for a genuine multi-year deep space mission today. They don't. What the evidence actually shows consistently across radiation science, closed ecosystem engineering, orbital debris statistics, and decades of human spaceflight medicine is that surviving deep space for years or decades isn't simply a matter of building a bigger rocket with more fuel. It's a stack of separate, overlapping problems: power, water, radiation, collision risk, bone density, cardiovascular health, vision, immune function, and psychological endurance, all failing along different timelines simultaneously, each one capable of ending a mission entirely on its own, with absolutely no backup plan once you're far enough from home that the word rescue simply stops applying. We built a space station 400 kilometers above Earth's surface, practically within shouting distance by cosmic standards. And even there, keeping a handful of astronauts alive requires constant round-the-clock support from thousands of people on the ground, continuous resupply missions, and a real, documented history of near misses from debris nobody saw coming until after it had already struck something. That is the safest, most heavily supported environment humanity has ever managed to sustain human life in beyond Earth's own surface. True deep space, the unsupported emptiness beyond it, removes every single one of those safety nets at once, and asks a human body shaped over hundreds of thousands of years for one very specific planet to simply endure the total absence of everything that body was built around. For years, with no way back if something breaks. It's worth sitting with that for a second, because it reframes something people usually take for granted. Every single thing keeping you alive right now. The air pressure you don't notice, the oxygen you don't think about, the magnetic field over your head deflecting particles you'll never see, the ozone layer quietly absorbing radiation that would otherwise be tearing through your skin right now. None of that is guaranteed anywhere else we currently know of. It's not decoration, it's the entire foundation everything else about being human is built on top of, and we get it completely for free, every single day, without lifting a finger. If there's one part of this that actually stuck with you, whether it's the 14-second survival limit, the way Biosphere 2 nearly ran out of breathable air over something as small as soil bacteria, or just how fast a healthy skeleton starts breaking down the moment gravity disappears, say which one in the comments, because the answers people give tend to be far more varied than you'd expect. And it's honestly one of the better conversations that happens under videos like this one. Space exploration isn't a dead end because of any of this. It's simply a problem we haven't finished solving yet, and understanding exactly how hard the problem actually is might be the most important first step toward ever solving it properly. It comes down to physics that doesn't bend for anyone, on a planet that happens to be doing an extraordinary, mostly invisible job of protecting every single one of us, right now, without asking for anything in return.